Welcome back to College Algebra, MAT 150. In this lecture, we will be discussing the very basics of graphing polynomial functions. So, in the last section, we talked about in behavior, and we talked about x-intercepts with their multiplicity. So, and what those ideas are. So what do we have to do to get a good, and it's definitely not perfect, graph of a polynomial? To get a perfect, we'll put that in quotation marks, graph, you really need calculus, okay, to determine how high and how low the humps are. But we can get a good idea of what these things look like. So to get this idea, we need three things. We need in behavior, we need the intercepts, and we need the multiplicity. This is usually the order that I go in, and I recommend going in this order, but you don't have to. Ultimately, you can do it in any order and get the same thing. But I will say that if you do the x-intercepts first, sometimes that can save you a step from doing the y-intercept. And we will see why actually in this very first example. So all we're doing is finding all this information, and then we're just doing connected dots. So you're just going from left to right, going from the next point on the left to the next point on the right. Another thing to note is that you have to be all of these are functions, which means they never curve back and go left, or curve back up, or curve back down. So you never will see anything like this in a graph. Okay, they're only ever just squiggles up and downs, and then you might have an arrow going up and an arrow going down or something like that. Okay, so you're playing connected dot, and you're trying to get it in the form like this, going from left to right. So let's see what we can do here. So we're trying to graph this function, negative 6x times x minus 3 times x plus 2. And what can we do? Well, we want to find the three things. So let's start with in behavior. This is something we did in the last section. We started discussing it. And we need to have something of the form, we need to look at each one of these. So negative 6x. Look at the leading coefficients there. That's to the first power, so times x. This is to the first power, so also times x. And we get negative 6x times x times x is x cubed. Okay? So our in behavior is we have an odd power, and then it's negative, so it's going to look something like this. So we're going to have an arrow up here and an arrow down here. Also, we need to talk about the x-intercepts. We're not going to focus on the multiplicity here. We'll talk about that in the next video. But for x-intercepts, remember we set the opposite variable equal to 0, which means our whole function in this case. So 0 equals negative 6x, x minus 3 times x plus 2. And then we have negative 6x. So we set each of these factors equal to 0. X minus 3 equal to 0, and x plus 2 equal to 0. And then so we have x equals 0, x equals 3, x equals negative 2. And then we get this back to being a point, so 0, 0, 3, 0, and then negative 2, 0. All right? And again, the multiplicity, we'll note that right now that these are all odd multiplicity, which we'll make note of in the future. But 0, 0, 3, 0, and negative 2, 0 are our x-intercepts. So 0, 0, we'll go ahead and plot these. 3, 0, and negative 2, 0 are here. And so I'll go ahead and, since it seems this actually has faded quite a bit, I'll go ahead and enumerate these. We have negative 1, negative 2, negative 3. I think I misplaced the negative 2 there a little bit. How about that? Okay. So we have something like this. And then we also need to find the y-intercept. And remember, just like with the x-intercept, for the y-intercept, you plug in 0 for the opposite variable. And this is why I recommend doing the steps in this order. And I'll show you why. Let's actually just go through and compute the y-intercept. It's important to recall this. So you plug in 0 for the opposite variable. So for the y-intercept, you plug in x equals 0. So that means we're evaluating f of 0, which is -6 times 0. So we're plugging in 0 for here, then 0 minus 3, and then 0 plus 2. But what is this? This is -6 times 0 minus 3 times 0 plus 2. But notice this 1, it's all being multiplied, but we have this 1, 0. Anything times 0 is 0. So we plugged in 0, we got out 0. Our y-intercept is 0, 0. Why is it important to do the x-intercept first? Because guess what? We already got 0, 0. And remember that because this is a function, we can't have more than one y-intercept, because if we did, it wouldn't pass the vertical line test. So I can't have a point here and then have another y-intercept up here, or down, or even also down, because then you'd have to be crossing, you'd have to be curving back to do this. And again, it also still just wouldn't pass the vertical line test even at x equals 0. So the point, the lesson from this is that if you get 0, 0, and it's only 0, 0, any other thing doesn't work. 0, 0 is the only thing that is both an x-intercept and a y-intercept. You can only ever have one y-intercept. And so if you have the x-intercept that's also 0, 0, then that is the only y-intercept you can have. So you can bypass actually computing the y-intercept because you've already found it. So if you don't have 0, 0 from the x-intercept, you still have to go through and compute the y-intercept. But if you do, you can just copy it down. So with that being said, I'm going to switch now to a pencil, just to be extra safe here. So in behavior is given by these arrows. So let's scooch this up. And we have these points right here. So these are our x-intercepts, and 0, 0 is also our y-intercept. It counts for both an x and a y-intercept. And the idea of graphing is you're just going from one, you're starting from the left, which as far left as you go is indicated from this left arrow, and then you're going as far right as you can go. So you're going towards this arrow. And you're doing so with, so I'm going to double down on all these points. Make them extra dark here. Okay? But you're going from left to right, and you're going from point to point. Okay? So you never actually have to start at where you draw the arrows. This is just a general indication of where the first arrow should generically be pointing. So for example, I'm going to this first point right here from this, basically from this kind of direction. And usually these are actually kind of steep, so I'm just going to usually start actually kind of close. So I'm going to remake this arrow here, and I'm going from here, and now that I'm at this point, I'm going to go through, and now I'm going from point to point. So I'm trying to draw this without picking up my pencil to go to here. Then I'm still crossing, and I'm trying to now go from this point to this point. And now I've done that, and then what direction should this finally be going to? Again, you're you're trying to connect a dot. You're generically going in this direction. Do you have to go to this exact arrow? Absolutely not. You're just going in that same direction of the arrow generically, okay? So we can erase this. And this is a pretty reasonable looking graph. Now, do we know exactly how high these humps are? Again, no. That is a job left for a calculus course, and that will usually be discussed in that course. But is this a reasonable graph given our limitations? Absolutely. All right. This is all for this lecture.